Hi everyone, I'm Vincent. This is my partners Sophie and Jake. We are the MechaniKids making MechaniKits for our senior design project. And so our project is to design hands-on activities for our mechanics classes here at Cal Poly. Uh, we were building, engaging, and inexpensive kits that students can get their hands on and start learning classes they learn through theory and lecture and then actually applying it. Hopefully this tests their understanding of the material and increases their motivation to learn. And so our design direction is to make one kit for each class. We're talking about general physics for the physics classes, introduction to mechanics, and then we're also making kits for engineering statics and dynamics. And each kit has these versatile manipulatives where they get to test different concepts for each activity. And the way we came up with these activities was through extensive iteration and testing throughout fall and winter. And in the spring, we are getting ready to manufacture these for the fall or winter of next year.
Just kind of piggybacking on what Vincent just said, here you can kind of see our design process. So this process gives a lot of room for different rounds of building and testing to make sure that our final products do work as intended and do have the effect that we want them to have. Here you can see we had in the fall, we did a lot of concept prototyping and we did our preliminary design review to make sure that the prototypes we were going to build hit on concepts that we wanted to at least test students on. And then this kind of shows what we did in the winter. We built and we tested, and we had 3 different rounds of that where we made statics, dynamics, and physics activities. And the testing that we did was actually in class with our senior design students. So they got their hands on our activities and they gave us feedback on what they liked and didn't like about them to make sure that our final design could be implemented as seamlessly as possible. What we couldn't do is actually do our final round of manufacturing and building our final kits as the shops were closed for the spring quarter. But instead we were able to increase our manufacturing plans and make sure that the shops could manufacture these kits and the final kits themselves without needing any assistance from us once we're gone next fall. Here you can kind of see our design progress. So we built and manufactured 7 different prototypes for physics, 6 for statics, 9 for dynamics. Through testing these prototypes, we were able to narrow down on 5 final activities for our physics kits, 4 for our statics, and 4 for our dynamics kits. I'll kind of jump into the physics kit since I was the lead for this. So we ended up with these 5 final activities. One of them is a vector demonstrator. In this activity, students can visualize vector components and resultant vectors. The next activity you'll see here is the force meter. In this activity, students get to play around with Hooke's law and actually calibrate the spring coefficient for a force meter. This activity is our movable pivot balance, and this illustrates principles of torque and tension as students try to balance the weights required on different ends of this ruler at different pivot points to make sure that the ruler is flat. This activity is actually a sliding friction activity, so students will slide a block down a ramp and they'll be able to measure the effects of friction on that block and how fast it travels down the ramp to calculate a kinetic friction coefficient. And then this activity here is an Atwood activity where students get to measure a static friction coefficient and also get experience using pulleys and tensions. And now we'll let Sophie detail the statics kits.
Yeah, so like Jake with physics, I took the lead on our statics kit. So this final design had 4 different activities in it. So that first one you can see is meant to tackle the concepts of torque and static equilibrium. So using that spring shown in the first picture, students will insert the spring at different points along the ruler and hold the system at equilibrium. And by doing that, they can observe the difference in spring deflection at different points, and then from that, infer the difference in force required to balance the system. And that second activity is a centroid activity. So using the composite shapes shown in the second figures, students can kind of calculate and find the centroid, or since it's a flat shape, the center of mass for these shapes, and they can try balancing it on that balance point and test whether they calculated correctly. The third activity is a simple machine activity. It can be set up two ways. The one shown has both springs, so that's actually an indeterminate system that the students can experience, or you can set it up with just one spring on that shorter output end, and then students can use those 3 different grip points to kind of observe mechanical advantage and then analyze the system as a simple machine. Lastly, there's the reaction activities. So this is kind of 3 separate miniature activities meant to just let students interact with some common reaction forces they'll experience in their statics classes. So we have rollers, there's some collars, we also have some things going on with hinges, and that's meant to show a force couple using those 2 hinges. So now I'm going to hand it off to Vincent, who's going to talk about our dynamics kit.
Yeah, so our dynamics activities consist of a collisions activity where they'll be dropping a ball down a chute and they'll predict how the system behaves. In that second activity, it's a swing ride activity, so it'll be modeling kind of an amusement park ride where that top part starts to spin, and then the riders will fly outwards, and so they'll be able to predict what happens with angular momentum. And in our third activity, they'll be rolling objects down a ramp, and they'll see which one hits the ground first. And so this is kind of an analysis on mass moment of inertia. And the last activity is a linkages activity. So they'll be spinning gears to see how the rest of that system is going to move.
So the impact of this design, we've ended up now with kind of 4 or 3 finalized kits, each with 4 to 5 activities that we've completed full manufacturing plans for. So due to COVID, we were not able to manufacture those kits ourselves, as I think Jake mentioned earlier. But now we are handing those off to the Cal Poly machine shops. So hopefully once the shops open back up, either next fall or next winter, those can be manufactured and be used in class by our sponsors. We've also created supplemental workshops that will go with each of those activities to aid students in understanding them, because we won't be there to explain. And there's the potential for these to be used both in class by professors or to be sent home with students and used for online-based curriculum learning. So the goal is that these kits continue to grow and be used for more classes. And then lastly, we'd like to thank everyone who's helped us with this project. There's a lot of people this wouldn't have been possible without. We have all of our sponsors on this grant, Drs. Vokos, Dr. Self, Dr. Molter, and Dr. Chen, who offered guidance on the curriculum for these subjects and have helped us along throughout and helped us test out ideas. Our Dr. Schuster is our senior project advisor who offered advice. And then lastly, just the Cal Poly ME department that's been a huge help to us throughout our time here. So thank you to everyone.
Thank you.
Thank you for your time.